What if I told you our entire universe might be shaped like a donut? Or that space itself could be twisted in such a way that traveling far enough in one direction eventually brings you back to where you started? This isn't science fiction, it's topology, the branch of mathematics that studies the fundamental shape of space itself. Today, we're going to explore one of the most profound questions in mathematics and physics. What are all the possible shapes that a universe could have? And remarkably, mathematicians have not only figured out how to classify these shapes using precise equations, but also given us the tools to potentially discover which one describes our own universe. Let's start with a thought experiment. Imagine you're a two-dimensional being living on what appears to be a flat surface. This is your entire universe. You can move in any direction along this surface, but you have no concept of a third dimension. Here's the crucial insight. Even though your world feels perfectly flat to you, the surface itself could be curved through higher dimensions in ways you can't directly perceive. Your flat universe might actually be the surface of a sphere, wrapped around a cylinder, or twisted into a Mobius strip. The beauty here is that each of these shapes has a unique topological signature that we can capture with equations. A sphere has no holes, a torus has one hole, and a Mobius strip has that characteristic twist that makes it non-orientable. These properties don't change even if you stretch or deform the surface. They're what mathematicians call topological invariants. This brings us to the classification of two-dimensional surfaces. Every closed surface can be completely described by precise mathematical relationships, captured in what's called the Euler characteristic. The fundamental equation is chi equals v minus e plus f, where chi is the Euler characteristic, v is the number of vertices, e is the number of edges, and f is the number of faces when we triangulate the surface. But here's the beautiful part. This number chi is a topological invariant. It doesn't change no matter how we deform or triangulate the surface. For orientable surfaces, there's an even more elegant relationship. Chi equals 2 minus 2g, where g is the genus, basically how many holes the surface has. A sphere has genus 0, so chi equals 2 minus 2 times 0 equals 2. A donut has genus 1, giving us 0. A surface with two handles has chi equal negative 2, and you can imagine surfaces with 3, 4, or any number of handles. For non-orientable surfaces like the Klein bottle or a Mobius strip, we get a different formula. Chi equals 2 minus k, where k represents the non-orientable genus, essentially counting how many crosscaps or twisted regions the surface contains. What makes this theorem so powerful is that these equations give us the complete catalog. There are no mysterious undiscovered surfaces lurking out there. Every surface is either a sphere with g handles attached or a sphere with k crosscaps, and the mathematics tells us exactly how to distinguish between them. The difficulty led to one of the most famous problems in mathematics, the Poincaré conjecture. Simply stated, it said that any three-dimensional shape without holes that's finite in size must be topologically equivalent to a sphere. It sounds almost trivial, but it took over a century to prove. The proof finally came in 2003 when Grigori Perelman used a technique called Ricci flow, essentially evolving the shape according to the differential equation partial g partial t equals negative 2 Ric, where g represents the metric tensor describing the geometry, and Ric is the Ricci curvature tensor. Think of this as letting the geometry itself change over time according to its curvature, like smoothing out wrinkles in a fabric. Perelman's work didn't just solve the Poincaré conjecture, it proved the much broader geometrization conjecture, which shows that every three-dimensional shape can be understood through one of 8 fundamental geometries. Each geometry has its own characteristic curvature equation, from the familiar flat space with k equals 0 to hyperbolic space with k equals negative 1. Okay, so all this geometry is good and all, but what does it actually mean for our universe? The mathematics gives us a catalog of possibilities, each with different observable consequences that we can express mathematically. The simplest possibility is that our universe is flat and infinite, extending forever in all directions with the familiar Euclidean geometry, where the parallel postulate holds and the sum of angles in a triangle always equals pi radians. But the mathematics shows us other intriguing possibilities. Another possibility is that our universe is a three-torus. Imagine a three-dimensional version of a donut's surface. In this universe, space would wrap around itself in all three directions. The topology is described by the fundamental group pi1 equals z to the 3, meaning you can wind around the space in three independent ways. There are even more exotic possibilities. The Poincaré dodecahedral space is constructed by taking a 12-sided shape and connecting opposite faces with a specific 36-degree twist. The resulting space has the remarkable property that its volume is finite. Approximately v equals 2.8 r to the 3, where r is the radius of the circumscribed sphere. If our universe has one of these finite topologies, then light from distant objects might have wrapped around the universe multiple times before reaching us. This creates what cosmologists call cosmic crystallography. We might see the same galaxy appearing in multiple directions in the sky, separated by specific angles that depend on the topology. For a dodecahedral universe, these angles will be multiples of 36 degrees. For a cubic torus, we'd see repetitions at 90-degree intervals. Scientists have developed sophisticated techniques to search for these signatures. They look for matched circles in the cosmic microwave background, pairs of circles that should be correlated if our universe has wrapped around itself. The statistical correlation function, c theta, should show peaks at specific angles theta corresponding to the fundamental domain of the topology. The current observational constraint is that if our universe is finite, its volume must be at least v greater than 2.1 times 10 to the 26 meters cubed. This comes from the absence of correlations in the cosmic microwave background data, which sets a lower bound on how large the fundamental domain could be. Every theorem about topology is, in a sense, a statement about possible universes. When mathematicians work out the properties of different three-dimensional manifolds, they're exploring the space of all possible realities. The Betti numbers, beta 1, beta 2, so on, that characterize the holes in different dimensions of a space are simultaneously abstract mathematical objects and potential descriptions of cosmic structure. This connection goes even deeper when we consider Einstein's general relativity. The Einstein field equation tells us that the curvature of spacetime is determined by the energy and matter it contains. But the topology, the overall shape, is a separate question that requires different mathematical tools. The Ricci flow techniques that Perelman used are now being applied to problems in general relativity, helping us understand how the shape of space itself might evolve over cosmic time. In an infinite universe where every possible arrangement of matter that doesn't violate physical laws should exist somewhere, a consequence of the infinite monkey theorem applied to cosmic structure. However, in a finite universe with volume v, there are only v over v Planck to the power of n possible configurations, where v Planck is the Planck volume and n depends on the number of particles. Current and future surveys are pushing these observational limits. The Planck satellite has improved our constraints on cosmic topology by analyzing this power spectrum CL of temperature fluctuations in the cosmic microwave background. Deviations from the expected pattern could reveal topological signatures. The upcoming Euclid mission and the Nancy Grace Roman Space Telescope will map the large-scale structure of the universe with unprecedented precision. If our universe has a non-trivial topology, these surveys might detect the characteristic patterns in galaxy distributions that would reveal the shape of space. Even gravitational wave detectors like LIGO and Virgo could potentially contribute. In a finite universe, gravitational waves might echo around the cosmic topology, creating interference patterns that could be detected in the strain data HT measured by these instruments. The universe's shape connects some of the most abstract areas of mathematics to the most fundamental questions about reality, from the elegant classification of surfaces through the Euler characteristic, to the profound complexity of three-dimensional manifolds described by the Ricci flow equation. Mathematics provides both the language and the tools to explore these cosmic questions. If you found this journey through the mathematics of cosmic topology fascinating, please hit that like button. It helps the algorithm share these ideas with other curious minds. And if you want to explore more connections between the abstract mathematics and physical reality, subscribe and ring the notification bell.